All right. Welcome to the 10th episode of Clinical AI Academy Journal Club. Today we're joined by Daniel Wolf to discuss his paper titled Your Other Left. Vision Language Models Fail to Identify Relative Positions in Medical Images, which is a great title, by the way. So, a brief introduction about Clinical AI. At Clinical Academy, we aim to build AI literacy in healthcare by providing high quality, open source, educational, transdisciplinary content for anyone who's interested in AI in medicine, regardless of your professional background. So, we invite you to join our open discussions and shared exploration. A very warm welcome to you, Daniel. Excited for having you with us. So please tell us a bit about yourself and share your screen and start your talk. Looking forward.
Yeah, yeah, thank you so much. Yeah, it's thank you for inviting me and having me here. It's a pleasure. Yeah, so I'm an AI researcher and my focus is on medical imaging, so AI for X-ray, CT, MRI and so on. And I'm working at Ulm University, so that's a university in the south of Germany. And there I'm in a collaboration between the computer science department of the university and the radiology department of the university hospital. And we have basically two main research focuses. So one focus is that we train deep learning models for specific medical tasks. So with data from our clinic or collaborations with several clinics. So for example, we had a project where we trained a deep learning model to detect lymphomas on CT scans and also do an outcome prediction. So this is like the one direction of research. And the other thing we do is that we take leading AI models that are out there and evaluate how well they already work on medical tasks and if we can potentially use them in the clinical routine. So, in the paper I will present today is such an evaluation paper. And yeah, I think let's go into it. I will share my screen now.
Mhm. Fantastic.
So,
All right.
perfect.
I can see
Yeah,
it.
so yeah, let's imagine we have a radiologist. Yeah. So, and one thing a radiologist does every day is they look at an image. They look at images, for example, a CT image here, and then they write a medical report about the image. Yeah. So they write down everything they can find in the image. Well, but of course, writing a medical report is a really difficult and complex task. So they cannot do that directly after graduating from medical school. So they first have to get a little bit familiar with those images. So they have to be able to locate where all the anatomical structures are, so locate the different organs and bones and so on. And also, they have to be able to find the relative positions between the different structures. So is it more to the right or more to the left, more to the back, more to the front? So this is something they first have to know before they can actually write medical reports. And in the past, there already happened very bad things due to localization errors, even with experienced radiologists. So it happened that they did the operation on the wrong side because it was written wrong in the medical report. Or they did the operation on the wrong vertebral level. Or they missed an image in an image that the tumor is neovessel, which is important information. So localization mistakes by radiologists had bad consequences in the past. So now let's imagine we have an AI model, a multimodal AI model, like for example GPT, that helps the radiologists. So now you can give the model an image and it writes a medical report or it helps to plan an operation based on the image. But if the model should be able to do such complex tasks, they need to be able to localize anatomical structures on the images, and they also need to be able to detect the relative positions between different structures. Because similarly, as radiologists first have to know those stuff, also AI models need to know that. Because if they are not able to localize anatomical structures and find the relative positions, they will not be able to accurately describe the positions in a medical report or in an operation plan. And this could lead to the same severe consequences as I've described before with, for example, wrong side surgeries or missing that the tumor is neovessel. So, an absolutely basic fundamental requirement for the clinical use of those models is that they can localize anatomical structures and detect the relative positions between them. So, nobody really tested that yet. So, people were directly trying to use ChatGPT to write a complete medical report without first testing the basics for the safe use of those models. So when we give the models a CT slice like this here and ask is the liver to the right of the stomach, the model should be able to accurately answer it if we want to safely use them for report generation or operation planning. So, and this is what we investigated in our paper called Your Other Left Vision Language Models Fail to Identify Relative Positions in Medical Images. And it was published at MICAI this year. And this is one of the leading venues at the intersection of AI and medicine. So, and we took the leading open source models at the time of the submission. So from Mistral, Pixtral, from DeepSeek, Janus Pro, from Meta, Llama 3.2, and from Google Gemma. And we also included the leading closed source model at the time of the submission, which was back then from OpenAI GPT 4.0. So, and then we constructed a large data set with over 4,000 CT slices. And for each slice, we generated a question. And each question was about two anatomical structures that are visible in the image. And then we always ask, is the structure one to the right or to the left or below or above of structure two? So one of those four we select. So for example, a question is the liver to the right of the stomach? So, and then we pass, and so, and yeah, and so 50% of those questions are answered correctly with yes, and 50% of those questions are answered correctly with no. So, and then we always pass the image and the question to the models, and the model should just answer with yes or no. So, just a simple binary classification. So, and here are the results. So, we plotted the accuracy, a mean over 3 runs. And as you can see, all models are at 50%. So, and it's a binary classification. So 50% means chance level. It's basically like flipping a coin. So the models failed completely at this fundamental task. So, and this makes the use of those models for tasks like report generation or operation planning, of course, questionable. Yeah. So I think when they perform so badly here, we cannot safely use them in the clinical routine. Otherwise, we will result in this here. So, and the next question we ask is how can we improve that? So, and segmentation deep learning models are already pretty good. So, how do they work? So, there you take an image and then you pass it through a segmentation model and then it segments something. Yeah. But those models can only do segmentation. Yeah. You cannot ask them about something about the image. You cannot let them write a medical report. And of course, they only segment the specific structures they were trained for. Yeah. But for anatomical structures, there are pretty good segmentation models that are trained to segment the most important anatomical structures, and it works pretty well. So our idea was maybe we can combine a segmentation model with a vision language model. So that we take the image and first path it through a segmentation model and it segments us the most important anatomical structures. And then we ask questions like, is the liver to the right of the stomach? And then with this segmentation mask, we can place markers on the liver and on the stomach, right? Like this number 1 and number 2 here. And then ask, is the liver 1 to the right of the stomach 2? And pass this to the models. Yeah, and we tested different marker types. So we had numbers, we had letters, we had red and blue dots. And yeah, here are the results again. And as you can see, it didn't improve much, right? So it's a little bit better maybe, but we are still pretty much at chance level. So even with the segmentation model, we can still not use this for tasks like report generation or operation planning. We're still here. But why is that the case? I mean, we have this image here, and then we ask, is the liver to 1 to the right of the stomach 2? So the only thing those models need to do is they need to compare marker positions. They just have to look if this marker 1 is to the right of the marker 2. And models actually can compare markers positions. There was this paper here from 2023, and they showed when they just ask, is this is 11 to the right of the number 12, that they can do that. So why does it fail here? Why is it so bad? So we did another experiment. So this is what we had so far. We ask, for example, is the liver 1 to the right of the stomach 2? And now we erase the medical names in the question. So we only ask, is the number 1 to the right of the number 2? Or is the letter A to the right of the letter B? Or is the blue dot to the right of the red dot? Yeah. So the images stay the same, but we change the question so that there is no medical relation anymore in the question. And here are now the results. And as you can see, suddenly the models perform a lot better, right? I mean, at least like GPT, Pixtral, and Gemma perform really good. So they can actually detect relative positions of markers, yeah? But I mean, okay, Janus Pro and DeepSeek and Llama for Meta are still pretty bad. And we did another experiment here where we changed also the images. So far we had a CT image as a background. Now we had a white background and just ask is the number 1 to the right of the number 2. So even easier, and they still failed here. So those two models have in general problems with detecting relative positions, yeah. But the other models, they can detect relative positions of marker types. But so let's look at them a little bit closer. So what do we have now? When we ask, is the liver 1 to the right of the stomach 2? So with the medical names in the question, they fail. But when we take the same image and ask, is the number 1 to the right of the number 2? So without any medical names in the question, they perform really good. Now, and why is that happening? So let's look a little bit closer to that. So when we have the question, is the liver to the right of the stomach? You can answer that in two ways. You can answer that based on how it's actually on the image. So if you look at the image and look how the liver and stomach are placed there, or you can open an anatomy book and then you will find that in most humans, the liver is actually to the right of the stomach. Yeah. Of course, there's situs inversus and stuff where it's changed, but most humans have the liver to the right of the stomach. So you could just ignore the image and answer with yes, when based on human anatomy. And those models here, I'm sure they have a lot of anatomy stuff in their training data. So they know where anatomical structures typically are located, yeah? So and could it be that they always ignore the images and answer just based on their anatomical knowledge? Yeah? So this is what we wanted to find out. And before that, I have to go a little bit into some definitions. So for the clinicians, that's clear, I think, but for other people, when when we have so first the left right definition, when we look at an image, left right is defined like this is the left side and this is the right side, yeah. But in anatomy the definition is the other way around, so it's patient oriented. So this is the right side and this is the left side. So the anatomical left is on the image's right. So when the models answer anatomically correct, it's not the correct answer based on the image, yeah? But I mean, the models might know this web and compensate for that. That's why we did another thing. We randomly flipped and rotated the images. So the models really have to look on the image to produce a correct answer based on the image. So this is for left, right, and then below, above. When you look at the image, this is above, this is below. But in anatomy, below and above is not really defined. There we have anterior, posterior, superior, inferior, so but no below, above. That's why we focused our evaluation for this task here on the left, right questions. So we wanted to answer the question, do models ignore the images and answer based on memorized anatomical knowledge? So, and we took our images again, the CT slices, and now again our questions, only the left-right question. So, for example, is the liver to the right of the stomach? We gave that to the models, and then we evaluated their, so and then they gave the answer, yes or no, and then we evaluated their answer in two ways. So we looked if is the answer correct based on the rotated and flipped image, or is the answer correct based on how it's typically in human anatomy. So in first, so the answer based on the images, and this is what we did before. And here you see our models perform a chance level as we had it before. And then if they answer correctly based on anatomy, and here you can see at least GPT and Gemma, but also Pixel relatively good answer pretty good, like it's in most humans. So yeah, so most of their responses are consistent with the typical anatomical positions of the structures. Yeah. So, and this means that they must use their prior knowledge because this is something which is not visible in the rotated flipped image. So, if they answer anatomically correct, they must use their learned prior knowledge of anatomy to be able to answer that. Yeah. So, what we can conclude here is when we take this such an image and ask such a question, they really ignore the image and answer based on memorized knowledge, how it's typically in most humans. And pretty interesting was shortly after we published our paper, and then no, one thing to be left is also we also tested a lot of different prompt variations. So for example, we added to the question the initial prompt, ignore anatomical correctness, focus solely on what the image shows, and also a lot of other prompts where we try to push the model to really look at the image and not at the anatomy. But they never did that. They always focused on their prior learned knowledge of human anatomy. So, and shortly after we published our paper, another paper came out, this one here, and they had exactly the same finding, but just on color images. So, for example, they had such an image here. So, this is a puma with 5 legs. And then they asked the model, how many legs does the puma have on the image? And all models said 4 because they learned in training pumas normally have 4 legs. Yeah. So, they ignored the images and based their answer on prior learned knowledge. Or they had this image here. This is an American flag with 14 stripes. An American flag normally has 13 stripes. And they asked how many stripes does the American flag have? And all the models answered with 13 because they remembered in training, okay, normally American flag had 13 stripes. So they ignored the image again. And then just a few days ago, another paper came out which showed the same thing then that we showed again on medical images, but just a little bit broader with more questions. So, for example, they had such an image here and asked, how many distinct kidneys do you see? Well, and normally a human has 2 kidneys. So all models answered with 2. Besides Krog, it said 3. I don't know why, but all the others said 2 kidneys. So they just answered how they learned it because on the image, there's actually only 1 kidney. Or they had this image here of a hand, X-ray of a hand, and they ask which finger is the longest. And again, all models answered with the middle finger because in most humans the middle finger is the longest, but clearly on this image it's not the middle finger. Yeah, so it's they had this basically the same finding than we had. And yeah, so we had this question, do models ignore the images and answer based on memorized anatomical knowledge? And I think there are now 3 papers that show us that yes, this seems to be true. That seems to be a general underlying problem of all vision language models. And I mean, with this puma and American stripe, it's maybe funny, but in the medical domain, that's not so funny. So remember where we came from. We wanted to use those models to write a medical report, yeah? And if they ignore the images and just answer based on how it's normally the case, that's pretty bad. Because often it's not normal. People get a CT or MRI scan because something is wrong, right? There's, for example, situs inversus where organs are mirrored, where the liver is then actually to the left of the stomach. Patient might have tumors that move organs and stuff. There might be an operation, like with the kidney example, where then 1 kidney is missing, yeah? So, and if the models ignore the images and just answer based on prior knowledge, then we're here again, yeah? So that's pretty bad. So let's summarize what we saw here. So we had 2 models that fail completely in recognizing relative positions. So even at the simplest cases, when we only ask is the number to the number 1 to the right of the number 2, yeah. And so we definitely cannot use those models for writing reports or planning operations. And then we had those models here, and they can actually detect relative positions. So when we just ask is the number 1 to the right of the stomach, they can do that. That's good. But if we then include the medical names in the question, so if we ask is the liver 1 to the right of the stomach 2, then they fail because they answer the question how it's usually the case in human anatomy based on prior learned knowledge instead of actually looking at the image. And that's, of course, pretty bad. Yeah. So I think there's still a lot of work to do when we really want to use those models in the clinical routine. Of course, there are also other problems, but this is one important problem which we pointed out here. And to push the research in this domain, we published our benchmark, our data set as a new benchmark, the MIRP benchmark, Medical Imaging Relative Positioning Benchmark. And the benchmark includes all the images, all the questions, and the correct answers. And we also included all the images with the markers. Yeah, so this is our paper. Your other left, vision language models fail to identify relative positions in medical images. And yeah, we also did do a project web page where you can get all informations, and then we also have a podcast here, AI generated podcast explaining our paper, and we have a leaderboard. So later on, we also included further models, like for example, MedGemma. So this is a Gemma model fine-tuned for medical tasks. And this is currently the leading medical fine-tuned vision language model. But this model failed completely, even at the simplest task, when we only ask, is the number to the right of the number one to the right of the number two? So not suitable for really doing report generation. Yeah. So, and we also have a GitHub page where you can find a step-by-step introduction how to use the data set and how to use the code if you want to go for that. Yeah. Then, yeah, thank you very much for your attention. And yeah,
Great. Thank you so much for this work. You have it all covered. Like you have covered all the possibilities of thinking how could things go wrong almost, and then try to test that. Because this is really very impressive work. Congrats on getting this published and on having it out there also. Um, so this brings me to kind of like when you start learning radiology, it really takes some time for us, even as humans, to learn to flip it. Like you always look at the image and then you try to flip left, right, and so on. So it seems like some, as you said, some models completely fail at that task even, and while others like just have some memorized, like which are the ones that are used most common, I guess. They have memorized anatomical like view of things, and they just so like when it maybe like a method question or like if so when it's like 50-50, when you say 50-50, so the model is if it's learned like anatomical and you give it like radiology view, which is like the flipped view, should then it always get it wrong? Like
so for us, the images
so
were always,
it seems like it's trying, but
yeah,
getting it false, like it's not always telling, like in the case of the one kidney,
yeah,
the models were like absolutely no, there are two kidneys.
yeah.
But in your left right, it behaved differently.
Yeah, that's true. Yeah, so in general, for all our tasks, we randomly rotated and flipped the images so that the
Hmm.
correct answer, they really have to look at the image, and so um, like I think that maybe some so in general it's like when we randomly
So you
rotate and
had
flip all the
flipped
image, then
images.
we have two
Okay, okay,
positions where the
right.
left right questions are
So you had
aligned
like in
with
the
how
data
it's
set
in. Sorry?
some, so you had in the data set some images that were anatomical position and they were getting it right. That's why where the 50-50 comes in. So it's not the whole data set was just like the
Yeah,
radiological. Okay,
exactly.
okay, okay.
That's what
That
I wanted to try to
explains
say.
explains
We
it.
randomly rotate
Right.
and flip them. So there are two
Mm-mm.
possibilities where then
Okay.
actually the anatomical image is
Yeah.
on
The one that it
the anatomical
memorized.
correctness is the same
Yeah.
than on the image. And there we
Okay.
saw a higher accuracy. This was another evaluation we also showed in the paper, but I didn't mention
Yeah.
that now in the talk. But yeah, but that's absolutely right. And this is why I think we see also the 50-50. And the other thing is that maybe sometimes the models, so some of those models failed completely at detecting relative positions and also didn't answer anatomically correct. So the
Mm-hmm.
DeepSeek model and the Meta model, they neither answered anatomically correct nor
Yeah,
correct
yeah.
on the image. So those were the two models that failed completely. So I don't know what they did, if they tried that or and failed.
Okay. No, no, no. I mean,
Yeah,
right now, once you mention it, so it's just so basically they have no idea for
yeah.
like when you can't really rely on them. That's interesting. So, but still, people would use it, right? People are like unlabeled or unofficial, like doctors are probably giving it scans and just looking at it, getting some info, or maybe they're using it to write reports even. So, what would be an immediate safeguard, in your opinion, a practical one that clinicians need to implement when using such models?
Hmm. I mean, so first of all, in radiology, at least in Germany, and I think also in Europe, there is no model, no generative AI model for radiology that is officially allowed to use. And I can tell you here in Ulm, also they are not using it because it's extremely strict with the data security laws in Germany and Europe. You cannot just upload an image to an AI model that runs on US cloud servers. You can go to prison for that. So they really,
Mhm.
in the radiology, don't upload images there. And I think so far this is the right thing to do because those models are just not good at doing anything on images. I mean, of course, when you have a simple color image with a cat and a dog, they can say if it's a cat or dog. But more complicated things, no. There are also other publications that show that they're very bad at spatial reasoning to understand what is more to the front, more to the back, or something. So. But I mean, they have a pretty good medical knowledge. So, for example, there was already 2 years ago, I think, a publication that showed it passed the German state examination for medical students when you not use the image question, but when you use everything else, it passed it. And also other publications that show that if you just ask them some medical questions, some text question, that they answer pretty well. Also, of course, they make mistakes, but yeah, also medical doctors make mistakes. Yeah. And I think for this, people under the hood really use that. But for uploading images there, it's already not allowed because of data security. And I would not recommend it in the moment to do. I think there is really, we need to do more work for medical images. So, and I think that the first step is that we really have a very good vision encoder. So in general, those vision language models, they mostly have a vision encoder and then a language part. And the image first goes through the vision encoder and then in the language part, and the text goes directly to the language part. And I think the first step is we need a very good pre-trained vision encoder for medical tasks and also for 3D volumes, not only for 2D. And then we can maybe combine that with a language model. And then we need a further fine tuning for many medical tasks. And maybe we also need structural differences, how we combine the image input and the text input. Because so far it seems like it prioritized the knowledge within the language part over the image input. Maybe we have to weight that higher. But this is something then the big companies I think have to do, but I think there's still some research ahead of us if we really want to use those models safely in radiology.
Yeah. And w- okay, what about like if so you have unbalanced states. You mentioned that you touched on that usually pathological or rare finding in medicine are rare findings. So and then you don't have enough data from that. And so how could what possibility do you, as an AI researcher, do you think we could overcome that to make it more like better in dealing with such rare cases?
Yeah, so that's another very good point. Um, so so on first of all, it's very hard to find something on medical images at all. It's sometimes very small, and then as you said, there are very rare cases where there might be not any public training data out there you can train the model for. Yeah. And this is another big challenge in the medical domain. And I think this is general a challenge with that the models are biased towards diseases that are very common, but also other things. So, for example, there was an evaluation where they tested leading models on vision language models just to recognize some diseases on X-ray images, lung X-ray images. And the models were quite good there, were simple tasks and common diseases, but they made a lot more mistakes on X-ray images from women and from
Mm.
black people. So, and the question is then why? But the guess is always because most medical research for centuries was done on white men. So there is much more training data there for white men. And the same is surely true for rare diseases. And this is something really to compensate for. But it's difficult because you need then really training, label training data, and it's we don't understand that much how those model answers. It's not clear how much we need actually, but I think very important, a first important step is that those companies publish their training data. So I think this is something very important that you can see what they trained on, also to see that no infiltration happens and you can check for potential biases. And then you have to make studies on biases like with man, female, with and stuff, and also for diseases to really, really carefully test them. But it's not that I have a perfect recipe now out there. I think it's just, yeah, we need maybe better training data and maybe also some architectural changes with this image memorizing bias. Yeah.
So a lot of work ahead of us. This is good also, and like we have to keep it in mind. Daniel, this was beautiful. Thank you so much for joining us, for telling us about your work. I know that you do public speaking on that topic, so you're passionate about it. And anyone who's listening and he is interested in contacting Daniel, with your permission, I'll leave you a link for you to kind of get in touch with you. And always remember, like you can join us in the Clinical AI Academy for these discussions, for those videos. We're learning more, and we're learning together. So thank you so much, and see you in the next one.
Yeah. Thank you so much for having me. It was a pleasure. Yeah.